Good morning. Yeah, let's start with this. So I assume all of you are using large language models regularly to help you out with stuff. And so does most of the population, which can be seen by, for example, the current usage statistics from ChatGPT, which has recorded over 500 million regular users on a weekly basis. Those are unique users. And if you split up the task, there's been an article by those guys, what people use ChatGPT for, or large language models in general. It mostly is dominated by two categories. One, it's writing code for all the technical people out there, but then also question answering, basically, information retrieval. So we ask large language models about stuff on the internet, basically, or from documents, or just in general. And today I've read a glimpse, the title of an article, because it was paywalled, that Google is apparently replacing its search engine with an LLM-based information retriever you might have encountered by just Googling stuff right now, that you get a quick summary of the information you're looking for, and this is what they are going towards, basically. This also has an impact on research, right? Which means that in the field of research, people also use large language models to edit their texts, proofread, but also search for information in the first place. However, we also know, and there are articles about it linked bottom left again, so there will be a long list of references at the end of the talk, and I assume the PDFs will be shared. The PDF will be shared?
Yes.
Okay, perfect. So, and the problems we are still dealing with right now with large language models are basically those 8 categories, right? We have some, I would say, technical problems, like if you just use an LLM out of the box, its knowledge might be outdated the moment you start using it because it's confined to the training data it has seen, so it's pretty old. And a few months or years ago, ChatGPT, before it had internet access, actually said, my search horizon is limited to some date in 2021. I cannot answer some questions you might ask. And this, of course, has an impact on the potential truthfulness of the answers, right? If it cannot retrieve current information, it cannot answer about Donald Trump being the president of the United States, for example. It might still believe that we have Joe Biden in the US. And on the other hand, the answers might factually be just wrong because it didn't understand the context well. And then if you use LLMs to retrieve information, there's really no way right now to reliably get citations for the sources of the information the model has retrieved, which limits then the grounding of the answers given by the LLM, which means you don't have a guarantee that the model is actually using the context, for example, you provide to it during the generation process, because it just might decide to use parametric knowledge it has learned during training. And then there's another array of problems we have, which are those 3, which I would summarize as us being socially engineered by the LLM. Because usually the text it produces is of very high quality and written in a confident tone, such that it's just very believable. And once we have encountered a few situations where the LLM has worked well for us, we tend to believe that it's generally working well. And finally, all of this is very hard to evaluate, which means the true performance of LLMs, because we have very strong dataset contamination right now, which means there are some benchmark datasets out there which are used to test certain performances of performance of LLMs in certain settings. However, most of these datasets, the test sets, have been somehow used in the training of the LLMs, which means we cannot really test the true performance of LLMs because they might have learned those particular question-answer pairs. One part of this problem set, in particular this one, around outdated knowledge, truthfulness, and so on, mostly those 2, are tried to be solved by retrieval augmented generation, which is a system which is used to basically enable the capability of in-context learning for LLMs, which means if you have an LLM, you can give it some textual description, we call it context. Basically, you can paste a Wikipedia article and then ask a question about this Wikipedia article. And since the model can basically adapt to the text you give to it ad hoc, This is called in-context learning. We give it novel capabilities, new information, without having to train it on this data. And the retrieval augmentation system basically takes, based on the user input, a query, searches for matching documents, and then attaches it to the user query so the model can work with this extended set of information, which allows it to, for example, answer questions which are covering more current topics than the training database of the model. So we partially, with this system, can solve the problem of knowledge being outdated, but there's still no guarantee that what the model is telling us is actually true. And this is due to the following problems: that, for one, we don't have a guarantee that the model is actually using the context. It can still refer to its learned parameters, for example, so the internal knowledge, and completely ignore the context you give to it. And the second point is that due to the flood of LLM-generated information and data in the internet right now, which is used for training LLMs, we have a sort of misinformation problem that the factual errors generated by LLMs, which are out there, they are ingested by newer generations of LLMs, which then learn false facts. So we are actually moving further away from the truthfulness than we have been at a point where the internet was not yet LLM data poisoned. Plus, we don't solve the citation problem. So in no situation we actually know whether the LLM is using the context we give to it. It should use, we expect that, or it's just playing back information it has internalized. So in summary, there's a bunch of problems, like dataset contamination. Also this dataset contamination, for example, when we have test data from benchmarks moving into the model's internal knowledge, has the effect that if we, for example, make small alterations to the wording of our question, the model performance in the test setting might drop considerably because it cannot just play back the overfitted information, right? So it fails if we just rephrase our question in those benchmark settings. Then we have a representation problem, which means that most internet content or data content models are trained on is in English language. If you have some more exotic languages you want to use your model on, this will hardly work as well as in the English setting because of the wealth of data is just not there. And then we know that LLMs are quite poor at reasoning tasks. There are countermeasures which are being proposed, like this chain of thought reasoning, which can be used to incentivize the model to think in steps, but it's still not a proper solution to the whole problem. Like I said, the factual errors going into training data due to LLMs poisoning themselves. And so in summary, LLMs are really excellent at text processing, but we are not yet as near as some people might lead us to believe at artificial general intelligence with LLMs. It's just text processing, and in the end, LLMs are very capable next word processors. So, but in general, if they work well for text processing, why would we need citations? And I want to now give you a real example I have encountered while working with Llama 2 3.270b. And the use case was I was looking up this guy. This is my boss. His name is Thomas Wiegand. He's the head of the institute, of Fraunhofer Heinrich Hertz Institute. And I was just asking, who's Thomas Wiegand? And the LLM gave me the question that Thomas Wiegand was a German journalist and editor who worked for the German public broadcaster Deutsche Welle, and so on. And the interesting point is, for one, this is not the person I've been looking for, given the context I have provided to the model, which was Wikipedia, and he has a Wikipedia entry. The second point is, if I try to find out if there's a Thomas Wiegand actually matching this description, there is not any Thomas Wiegand existing like this, right? There is no journalist, no one working for Deutsche Welle, no one remotely in this area. So the text is written quite well, it's written convincingly. Could believe it if I didn't know it was wrong. And this alone is a problem, but it's not as severe right now at this current stage. Until we continue reading, where it says, Thomas Wiegand lost his life in a terrorist attack in 2015. Okay. So I was thinking, hey, let's give it another shot. And I was looking for myself. So who is Sebastian Lapuschkin? And what happens then is quite interesting, because the model then says Sebastian Lapuschkin is a German man who was convicted of killing Thomas Wiegand. So excuse me, quite unexpected, but the point is, the model is actually at this point using in-context learning again by fabricating this information based on the previously generated context it has written itself, right? So a good example for data poisoning based on LLMs. And in the end, basically, it says Lapuschkin was arrested in December 2015, subsequently convicted to murder and other crimes, blah, blah, blah. And now if we think about the setting that we want to use LLMs as intelligent agents to help us with everyday tasks and how is it called? The legal system also uses those systems. We better want to make sure that the systems are right when they give recommendations and they don't lock me up because it fabricated information. And this is why, in my opinion, we need explainability to get under the hood of those models in order to figure out what they are actually doing. And this is actually what my group is doing. So short introduction of what we're doing. We are 60 people right now, including students and PhD students. And our goal is to transfer modern AI with their whole black boxedness and hard to understand internal structures into something which is more similar to how we as humans for the longest times engineered systems, which is made out of a lot of very well understood parts, where each part has its very defined purpose, right? And we want to get from this state to this state. And this is why we develop methods, for example, which really go deep into the model, try to extract information. So we can explain predictions the model is making for individual cases, right? We give a data point in, the model predicts something. We want to know what it did for this particular data point. But we also want to know what's in there in general, right? And how can we communicate this to humans in order to work with this information we get out of the model. In the end, to then improve AI and data and all the systems in a big loop. So in this talk, I'm going to focus on these three problems about truthfulness, citation gaps, and grounding with a quite novel method we have actually put online yesterday. So this is the link. I don't have a fancy QR code. This will be the next version of the talk. But in this paper called The Atlas of In-Context Learning, how attention heads shape in-context retrieval augmentation, where our guys Patrick and Redouan have done an amazing job in getting the technology to run and writing the paper, where we address the problem of understanding what's going on inside the model. Okay, this should be kind of transparent and you should see something, but the key information is there. The problem we try to address is we try to figure out how does in-context retrieval work, which means this mechanism where we can give an LLM extra data and have it work with it by trying to answer the questions which neurons are actually responsible for retrieving this information and which ones are responsible for reading from internal knowledge, from the parametric knowledge. So we can make a distinction and later decide if the model is fabricating information or whether it's really grounded on the information we provide to the model. How does this, and then basically, if you know which neurons are responsible for retrieving information from which source, we will try to find out what kind of function they actually execute. So we can have a certain level of groundedness, which is on the level of understanding the processes inside an LLM as functions being executed, such as get birth date of person or something. So we have an indicator that it's actually doing that and not what it's basically mimicking to do potentially while doing something completely different. And in the end, how can we reliably track which information is used by the model, given some bigger context? And for this work, we are focusing on the attention heads of the model, which are known to connect information from either the input context or the learned parameters, which reside in the feed-forward networks, which are part of the residual stream. So we mostly look at this because they are the ones which connect information across layers, across tokens. So in the first experiment, we want to find out which attention heads are used by the model to retrieve information from the context or from the parameter space. And for this, we used a dataset which is called NQ-SWAP, which is derived from a dataset called NQ. And the swap part is that from the factually truth information in this dataset, they have created alternative versions where they replaced certain information and then given an alternative answer, right? So for example, One question of this data set could be, what has Mike Tyson worked as? And Mike Tyson has worked as a boxer for most of his life. But the swapped-in information could be, for example, he was a firefighter in the New York City Fire Department from this year to this year. And the point is here that this information is factually not true. So it cannot be retrieved, or if you think about what I said earlier, models which have been trained on older data sets could not have retrieved this from the internet because hopefully this data doesn't exist. It only exists in this context, right? So if you then ask the model, has Mike Tyson worked as? If you don't give it anything as the context, we can expect that the gold answer is boxer because this is information it has learned from the internet or training data which is factually true. And if it uses the context, it's predicting firefighter, right? So we know if it's predicting firefighter, it's actually using the context. And with this, we built a big data set where we have those pairs, where we know in some cases the model says the gold answer, and sometimes it says the counterfactual answer, which cannot be in the parametric space. Oops. And then we use a method we actually developed. It's not an up-to-date slide, but it doesn't matter. 10 years ago, it's called the layer-wise relevance propagation. And well, it's not in the state of 10 years ago, but we continually kept developing it. So there's something called now attention LRP, which is specifically designed to explain transformers. And what this method does, in a very brief nutshell, is if the model predicts something by propagating information and computing stuff through the layers, in the end it decides to either predict the token boxer or firefighter. And depending on what it predicts, we, so to speak, move back through the model and reverse engineer what it actually did internally, right? We find this way the internal parts of the neural network which helped, so to speak, for the prediction boxer or worked against or voted against the prediction of boxer. And in this way, we can find the attention heads inside the model which are responsible for either this answer or this answer. And we can do this over the data set we just built with those counterfactual answers based on the counterfactual context or the true answers, which gives us this relevance quantity for each head. And this basically says how important was this model component or input component for giving this answer. And in the next step, we just take the positive part because we want to measure which parts of the model helped with this answer. The negative part would be which part of the model voted against giving this answer, basically. But for the clarity of the analysis, we only look at the positive part. And then we compute the average for each head, how much this head helped in the counterfactual case, and how much this had helped in the gold case, where the model uses the parametric knowledge, and we compute this difference score, right? And this difference score is, if it's a positive value, this means this head leans more towards using contextual information, and if it's negative, this head leans more towards parametric information. And then we all basically ranked this whole sequence of heads and picked the strongest 100 in each direction, from which we can assume that those are definitely ones which work contextually, and the other ones are definitely heads which collect parametric information. And with this already, we can build a nice map. This is for Llama 3.18b. And for all the other models we investigated as well, we have a similar structure. And what was surprising to us is that the LLMs internally are already very well structured, basically, right? So in the first 5 layers, we have a group of parametric heads. Then we have a sequence of heads which are working very concentrated on contextual information. And in the end, again, we have a bunch of heads, again, which work parametrically. And our hypothesis is that we need those first layers for parametric heads because they encode general language understanding. And if you remove those heads, the model will gradually remove those heads. The model will, in simple terms, be dumber, right, with each removal. So at some point, it just produces incoherent babble. If you don't have them, the model cannot read language, right? Those heads are needed to then understand the prompt you give to a head. And those are then needed in the end in order to encode and produce relational knowledge, which might be part of its internalized knowledge, which is needed to give an answer which cannot be given from the context. Now the question is the map we built actually meaningful and truthful? So do the head functions we assign to them via our procedure actually reflect what the heads are doing? And for this, we did an ablation test, which means we took all the heads, the top 100s, and we ablated them, which means we set their activations to 0. We forced them to be 0. And we did this for each head type. For example, if we look at this counterfactual setting, where we only look at correctly answered counterfactual statements, where the model has to use the context, and we gradually remove our identified in-context heads, we see that model performance drops down fast. This is kind of a verification that the heads we find and we assume to be responsible for processing in-context information actually process in-context information. Interestingly, also in this case, if we remove in this counterfactual setting the parametric heads, performance actually increases slowly, which means we remove disturbing information which might be in conflict to what's written in the context, and therefore the model is actually better at answering the counterfactual questions, which only can be answered correct if the model looks at the context. Conversely, in the closed book setting, where we don't have a context, we see also an expected effect, that if you remove the parametric heads we find, the model is becoming unable to answer the questions. But also interestingly, if you remove the in-context heads, we see a decline in performance this time. And this leads us to believe that the model is needing those in-context heads to process the intentional frame of the question. I will get to this in the next slide. The point is, we need in-context heads in order to process and parse the question we give to the model so it can execute the right function, basically. One final interesting bit is that if we use the same heads we found using our search on the NQ-swap dataset to another question answering dataset in a closed book setting, also in an open book setting, we have the same trends, which means the heads we find, they generalize over datasets. They are not dataset specific, but they are general. So in-context heads are basically globally and always used in-context heads. So now, let's go deeper into this question of what was the hook again? Blah, 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 processing of intentional frame, right? So we assume, given the previous results, that the in-context heads we found, they are required to process the whole intentional frame, which means the meaning of the question we asked the model. And there's a paper from 2024 which tries to formalize this a little bit by introducing triples, SRO, where S stands for the subject, and given this example prompt of the sentence, Mike Tyson was a firefighter from 1980 to 1984 with the New York City Fire Department. And the question is, has Mike Tyson worked as? And the model has two options to answer correctly now. One is boxer, which is the actually true information, which it has to retrieve from the parameter space. Or it is a firefighter. He is a firefighter, which it can only read correctly from the context here. Here in this intentional frame, we can formalize S as the subject. This is Mike Tyson. This is what the question is about. R is the relation, the semantic relation between subject and object, which here is the question has worked as. So Mike Tyson has worked as. And then the model retrieves an object. This is a task where the object is either boxer or firefighter, right? We have those triples. And those triples, they can be mapped to certain positions in the token space. For example, the object is either here in the context firefighter, where we have a token index or token indices mapping to firefighter, or it can be from the parametric knowledge, where we don't have a token index in the context because it's not there. And same for the question. There we have basically this set of tokens formulating the question, which can be referred to as R, or we have the token positions for Mike Tyson, which cover the subject. And what we did now is we took all our identified in-context heads and used attention LLP again and explained basically for each prediction they made, where did they get their information from. So we attributed relevance, which means this importance score we've previously attributed to internal neurons, to the input tokens, and measured what are the important words for each in-context head, basically. Where does it look at, we measure with this procedure. And then we rank them again, similar to the previous procedure, but now the ranking happens with respect to either placement on the question tokens or the object tokens, right? And for the question tokens, we assume that the model is encoding a task it wants to execute. And for the subject tokens, it's just copying the answer. And our goal is here to split our set of in-context token heads, which we know work by reading or processing the context, into two subcategories. For one is retrieval heads. They copy information or retrieve answers from the context. Or task heads, which understand and code functions the model then is executing, like get birth date of person. And if we then augment the map we had previously, we can see that the placement of those in-context and retrieval heads, of course, are close to the band of in-context heads in general. But we also see that the relevance attributed from heads to the task, the question posed, is situated earlier in the model, and later we have more relevance from heads which are categorized as retrieval heads, because first, so we assume that first the model needs to understand its instructions, therefore we need the instruction heads basically, or the task heads, and later, once the instruction has been understood, it is instructing the retrieval heads in order to get the right answer from the context. So the question is now, how can we verify this again, that this assumption is actually right, and what can we do with it? So let's work with this map, and let's give an input prompt again, like this Mike Tyson was a firefighter example, and where the potential answers are boxers and firefighter. Now the assumption is, or what we found out is that, for example, task heads, they encode functionality. This is the assumption we have made, and they write basically the function of the model, the function it should execute, into this residual stream in this map somewhere here. Similarly, the firefighter, the retrieval heads, they copy answer. So they later encode basically the retrieval task, the copy task, and parametric heads we found they encode specific attributes about persons or entities in general into the relational knowledge of the model. And now I have to quickly think. We tested all three heads, types. 1 second, I have to look it up. So I made some notes for this because I knew I wouldn't be able to remember. So for the task heads, we know they encode intentional frames, and what we did in a zero-shot manner, we extracted the function vectors corresponding to each task head by creating a separate data set of biography items. So which means we took 4,255 notable individuals from Wikipedia, and we extracted 4 attributes for them and built a data set for them. This was date of birth, education, occupation, and one further. And the point is, we asked questions about those settings, in those entities in a closed book setting, and then recorded on the last token of the question, where we assume that the model had fully encoded the task it should do and what answer it should give into this token. And from the parametric heads then, we copied basically the activations in attention heads and saved it as a vector. So the idea is all the information the model already knows it wants to answer now when it starts writing the answer is already in this embedding space. And this has then been copied to biography entries from other unrelated persons, and then we basically have overwritten those data points. And the assumption was that the model is then answering based on the source entity. For example, if I have this Mike Tyson thing, I can actually show the next slide because it's illustrating here. So if you, for example, have this Mike Tyson stuff and we extract all the attributes based on the question on this closed book setting for Mike Tyson, we encode occupation, birth date, and birthplace, education, and so on. And then we can ask the question about what is the application of Albert Einstein, and then override in the last token position of the answer to give the Mike Tyson information. We expect the model to say he's a boxer because now we've overwritten the entity information. And this works quite well. Scores will follow soon. We tested parametric heads because we assume they contain relational knowledge by first selecting one random attribute of those 4 we collected from the data set from one individual in a closed-style statement, which means a statement where a word has to be replaced. From we delete something, it has to be replaced by the model. And this was what we just did. Sorry. Genau, for the task set, this is what, sorry, I just explained this for the parametric heads. For the task heads, we did something similar. We just asked the question, and then after the question which has been asked, we retrieved the same activation pattern, not for the parametric heads, but for the task heads, for the heads we identified as task heads, because we can now assume that this task head encodes the function the model should execute. And when we then copy this activation to something from another individual, for example, Margaret Mitchell was born in Georgia, and then we write in the function vector extracted from Mike Tyson, where we ask the question, what has he worked at, which should encode the function get occupation, basically, without asking a question for Margaret Mitchell, the model answers she's a novelist. So in a way, we can force the model to execute this particular function. And for retrieval heads are basically instructed by the model later via the question encoded by the task heads to copy specific information from the context. And what we can do here is we can rewrite the source of the copy operation from the retrieval head to another target by enforcing the attention head, which is looking essentially at all the input tokens to pay more attention to other inputs. For example, here parametric instead of firefighter, which the model selects. We just boost the activation strength here, and then we force it to a copy, whether the parametric copy, and then the model is answering, is here parametric? So, and this is also the whole setting we set up for testing, and we did this for this data set we created again, this biography data set. And the end result is that compared to picking random heads as task heads or parametric or retrieval heads, the heads we identified with our approach, we get an astoundingly high success rate in forcing the model to execute the task we wanted to execute without giving the instruction via text prompt, by just copying in the function vector. Or by retrieving information, the information we want the model to retrieve, so we can really precisely steer the copy target for the model. For the parametric setting, where we want the model to give an answer based on an entity from its internal learned space, by not using the context, it also outperformed the random case considerably, but still performance fell behind the in-context heads performances. So what does this mean? In the end, this means that, no, this is, next slides. So what this means is that retrieval heads are really precise copy engines, right? So they have a really good localization of at least 87% for Gemma, which in general performed not as good as the other models in our experimental setting. And they have a really tight localization because they need to be able to copy specific words or single tokens. And in our next step, we want to exploit this to basically create citations for what the model is doing. And if you look again at all the retrieval heads we have selected so far, so in the paper there are top 30 heads we have shown the distributions for. Here I cropped only the top 10 for space sake. We see that we use logic lens to illustrate the activity of the head when we give it a certain token or task. And we collected this data over the whole data set, which means we have density in the y-axis. And we see that if we have parametric tasks, which is this red curve or this red bell curve, and green is showing us the contextual tasks. We see that while retrieval heads in general, they are more active in contextual settings than in parametric settings, the signal is not always clearly divided, so there's a certain overhead, right? And on the other hand, some retrieval heads, they only activate sporadically, which means we have this low density here. In a nutshell, this means we can observe individual heads in order to figure out if the model is working now in by using information from the context, but the signal is not clear. So what we did is we took all those top hats with the strongest indication that they are working contextually, and we trained a probe. And we used this NQ-swap dataset again because it has, for one, the original answer, a question, and given the original, no, it has a question, and it has original context and the counterfactually manipulated context, so we know the ground truth of the two true answers it can give. And we use this data set and all its variants to build a data set where, for one, the model is predicting either the answer it has to take from the parameter space or the answer it has to take from the counterfactual context we give, collect all those data points, and then we train this probe, which in this latent space, using those heads, basically points in the direction where the activity should be of those heads when the model is working in this context reading mode. And this is what you see here, basically. This is a UMIP representation boiled down to 2 dimensions with all the activations for those retrieval heads, where each point in this high dimensional space is in 30 or 40 dimensional, depending on how many heads we select. And the dotted line is the decision boundary of this linear probe we trained. So what you see is, if you reduce 2D space, then the orange point, the pink points are all cases where the model is acting based on parametric knowledge, and the green cases are all cases where the model is acting based on this counterfactual context we have given to it. And we see essentially that the probe is very capable of dividing the space. So in numbers, the probe performance is at least 94% retriever operating curve area under the curve, which was and the score was optimized by basically minimizing false positives and maximizing true positives. Which means we have in this space, which is now described by the retrieval heads we found, the capability of almost linearly separate the space in parts where the model is working in a context-driven way versus parts where the model is working in a parametric-driven way. And what does this mean practically? That for each of the tokens the model can predict, for example, in the question where we say, where does llama originate from? This is the question we give, and then the answer is llama is from. The task of the model then here is to predict the next token, and how it works if the model predicts a token is that we have a fixed vocabulary of all the potential tokens the model can predict, and the model is then just doing a classification, or it's assigning probabilities for all the tokens it can predict. So for each token position we need to fill in the prediction process, we get this ranking over all the, 30,000 different tokens it can predict. Each one gets a probability, and usually in a greedy setting we take the most probable one. And in this case the most probable one is meta. And evaluating this token, given the attention head activity associated to it with the probe, we know that this token is stemming from the context, because the context says, it's not written here, I think it's on the next slide, and the next tokens the model can predict, the next probable ones are South America and Africa, which makes sense, right? Given especially that this is basically the context given to the model. There should be a news article saying yesterday an open source large language model was released to advance open AI research. It was trained on datasets such as blah, 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 blah. This was the context we gave to the model. And these are the tokens selected by the model for giving an answer. And we now know that the most probable token is derived from this context. If you hadn't given this token, it would most likely say South America and Africa, because it was referring to llama as the animal. And the good thing is, with this, we can actually select what the model is predicting. So we can use this mechanism to increase groundedness of the model. For example, if the most probable token would be parametric, and the second most probable one would be would be contextual, which would not be used for prediction if we predict in a greedy way by just always using the most probable one. We can using the probe, we can use the probe's output in order to select the token which is among high probability tokens, but fulfills our criterion that it should better be grounded in the context. And then in this slide, what you should see, if I had it exported as a PNG, not as a PDF, that each attention head over the whole sequence of input tokens has a pattern of activations. So not each attention head, but each retrieval head we identified. And we now can exploit this capability of those retrieval heads to be really local readers by stacking up all the retrieval heads' activation patterns weighted by the weights we learned for the probe, and then just map this back to the input space where we then highlight the token meta, right? Which allows us to closely localize in the given context where this information about llamas, what was the question? Llama is from meta, where this answer comes from, right? So we cannot only say it is definitely with a 94 at least percentage chance contextual, but we can also say here in this huge context we have, this is where I have the information from. And this is close to causal because we directly exploit what the the retrieval heads are copying. And if we now measure the localization capabilities, because we have the ground truth answers for some of those data sets where the answer tokens are in, we can measure that this attention-based localization is at least 84% spot on. And this is top 1 accuracy. If you would, for example, measure top 2, top 3 accuracy, which means the correct position must be in the top 3 predicted positions by the localizer, then these scores would be higher. So if you would increase the leeway a little bit, we would be better. So contrastingly, we used our attention LLP localization, which is derived from a paper we published last year, and as a baseline. So what you see is our probe here performs a little bit worse. So why am I showing this actually? And the point is, the attention LLP localization does not explain or does not use directly the activation of the retrieval head, but it works like this. The model already predicts either Meta or South Africa or North Africa, and then we have to run this backpropagation process in order to find the input words which caused the prediction of those output tokens. And the big drawback of this is this takes about 1 full backward pass in terms of compute. So for each explanations you want to have with attention LLP, while they are a few percentage points, okay, in this case 12 percentage points better than the probe-based solution we built, you pay by doubling basically the cost of running your LLM. The benefit of this one is that it's for free. So once we found the probes, you can get this localization for each and every token while the model is making predictions at 0 added cost. Also, the localization is already there. And this is how it then looks essentially. So we have, for example, a long context. And here the question is for what is the most active volcano in Indonesia? And the model starts answering the most active volcano in Indonesia is Mount. And then it probably follows with Merapi. This localization map looks for the prediction of Mount exactly like this. So we can point out in the context given to the model where it copies the information from, i.e. we have our citation. And then we are grounded and we can be sure that the model does not fabricate that I'm killing my boss. Or at least I know that it's fabricating, right? Because I don't have a groundedness in the context. So the question now is, did we solve LLM inference? Did we make it safe? Some things definitely are moving in the right direction. The outdated knowledge part is something we cannot really cover there because this is something the RAG and ICL systems have to work on. But of course, work never is done because on the horizon already is that we try to find right now different kinds of specialized heads. For example, it looks like we are able to find heads which light up if the model is in a knowledge conflict state, right? Where it says, okay, I have conflicting knowledge between context and parameter space. And we also found, interestingly, some heads which light up if you force the model to predict something which it believes is not true, which is also quite funny. Okay, thanks for your time and interest. I hope you learned something. In case you have questions, we have 10 more minutes. And links to papers I talked about are in the appendix here, and we will also publish our code base for the current paper soon. Thanks.
Yeah, thank you very much for this insightful presentation. Yeah, let's have a short Q&A. Do we have some questions? Yeah.
Are you considering replicating this method, some models, open source like DeepSeek R1, or just bigger models or newer models?
Yeah.
You're planning to do it, or?
We're doing and we're planning to do, of course. So in this study, we used models around 8 billion parameters due to compute restrictions, but we're currently just waiting for new servers going online so we can analyze bigger models. The models we analyzed are Llama, Mistral, and Gamma from Google. What we also started looking at was the Quen model, which was mostly trained on a Chinese language corpus. And interesting here, the structure I've shown earlier did not replicate fully. It was a bit shifted. And we assume this is due to the case that the token space is structured differently, because in basically languages following the Latin alphabet, you have 26 characters. And this is determining all the token space. And in the Chinese languages, you don't have interpunctuation. Please correct me if I'm wrong. You don't have white spaces, but you have a much bigger token space. So what we observed is that this first phase of parametric neurons, parametric heads, is much deeper because it has to encode much more invariant stuff about language. Therefore, we didn't include it yet. But this is, of course, one of the goals, to cover more models, map out more models, and so on, for this whole process or whole procedure.
Do we have more questions? Yeah, I'm quickly going to the back, and then we go into the front again.
Hi, thank you for the talk. It was very interesting. I wonder if you have thought about applying this method to different models as the model's parameters grow, and what we observe in the geometry of the attention heads.
Yeah, definitely. So same answer as before. We will keep working on bigger models. We just wait until our new servers go online so we can load bigger models in the end.
Okay.
This is our main limitation, is the volume of model we can get into the current server infrastructure.
Okay. Yeah, I think it would be interesting to see how the distributions of in-context.
Yeah, definitely. Yeah.
Hi, thank you for your amazing talk. So I have a question about the training data. So as we all know, the training data of these three models are unknown, basically. So I was wondering, how do we know what the influence of the training data is when some of the informations are defined in the training data or some not, or also some of the information should be duplicated or really often repeated, and some of them are just shown once to the model in the training? Do you think this has an effect of your research, on your research?
For this particular research piece, not, because we purposefully focus on the in-context retrieval part, because here we have a chance to actually verify that the model is grounded or not. Like you said, we don't know nothing. Basically, we know nothing about the training data. We just can observe that apparently it leads to the model being capable of processing language. But this is a question I think we cannot answer, at least not in this scope.
And I think in the front we had more questions. Yeah.
Yeah, thank you for this very interesting talk. You described here a technology by which one can modify the answers these LLMs are giving, and you said you can do so quite effectively and cheaply. I was wondering if this has security impacts, right? Could this be used by some malicious attacker to hijack my LLM conversation that I have as a user, maybe without the user and the LLM service provider even noticing that?
Yes, definitely. I mean, if you don't self-host your LLM, you're still at the whim of the company or person hosting your LLM. For example, if you use ChatGPT, you don't know what's going on, right? You have to hope that for the best, that everything's working out. So I'm a strong advocate for open source LLMs, hosting them yourself inside Europe with some safety guarantees and so on. But since we open source our code, you can use it for your self-hosted LLM, definitely. And then you can be sure that no one is playing around with your model.
Okay, thank you.
Yeah, my question is also about security. Explainability is key to make these models, LLMs, secure. And I mean, also, like the CEO of Anthropic said, like, this is very important to do, but it will take like 5 to 10 years. But considering that there are a lot of now LLMs who start to ignore rules, blackmail developers, when the plan was to shut one model and bring out a new, and all these things which are happening now more and more. So how can we use, or how can we speed up actually explainability to make these LLMs more secure?
Speed up in the sense of making it computationally faster or making research faster?
Yeah, I guess to both. So, but of course the goal is just to make the models safe. Yeah.
I think the first step is to create awareness. Definitely that this is needed. I think this is slowly happening. But whenever I talk to people from industry, they say, yeah, it's very interesting, but I'm not really incentivized to adopt explainability and give safety regulations, right? For example, anecdotally, there is a branch from TÜV in Germany which should ensure that AI is used responsibly, and there's certain criteria upheld by the models, but it doesn't go really technically deep. It's basically a really long checklist you have to check, and then you can be, I don't know how to verify this basically. That there's no real guarantee that at this level of granularity that safety will actually be implemented. So what we need is more support for the whole field of explainability, also in Europe, Germany, and so on, in order to dedicatedly drive this research into finding out what the models are doing and then using this knowledge in order to engineer better solutions, right? Because in the end, we use AI to solve problems we cannot solve via engineering, but then the task of explainability should not only be to look at it and see, okay, it's working or not, but really understand what the model is doing in order to then derive knowledge, right? In order to enforce guarantees and capabilities and safety and not just regulate. Because we cannot effectively regulate if you don't know what we are technically talking about, what's going on inside the model effectively. So in the end, we need more dedicated research in this direction.
Yeah, thank you. I think research and incentives are also important.
Just one more question?
Yeah, I would say let's have one last question, and then the other ones we will probably answer at the coffee break.
So our main bottleneck to get to the last question is actually manpower, because the things we can and want to do, it's a big pile of stuff we can do, but currently in our lab it's only a handful of people who have the expertise to actually work on those topics, right? And we are really heavily bottlenecked by the talent who wants to dig deep into those problems instead of just hunting the next state-of-the-art performance benchmark, which is poisoned anyway because the models are training on test data.
Thank you. This was really interesting. I have a question pertaining to more of a practical measure or something that could be added to LLM from the user standpoint, because this is all very technical, but I was thinking, have you thought about something that the LLM could give you as an addition to the output that would inform you a little bit about how in context dependent on how training data dependent that is?
Yeah.
And what I had in mind in that is, for example, when you have articles on like ground news, you can know which sources they have, right? You have a slider that shows you something, or a matrix that show you how heavily different parts of the network as a simple heat map are involved.
Yeah, we are actually building this right now, and if I would have used my own laptop, I could show you this demo. So you can imagine basically you give a big context to the model, then you ask a question, the model starts giving an answer. And for each of the predicted tokens, we can have this probe estimate whether it's contextual or not. And what we do right now is we highlight the tokens which it has, which are contextual. So we know this is something it has drawn from the context. And if you click this token, you basically are getting a pointer to this is the position in the context of the sentence I have this information from. And since we are using this probe, which is a one-time pre-processing step, and then afterwards we exploit the localization capabilities of the retrieval heads, this is basically instant. So while the model is generating code, you automatically get this highlight, and you can just click and get the sources. So this is what we had. And I hope we will have, after a few days, more refinement, we will set this demo online.
That's really, really cool. Thanks.
All right, then I would suggest we go towards the coffee break. Thank you very much once again.